M mode. So that's the transverse magnetic mode, transverse magnetic solution. So it's the guided transverse magnetic modes. So this is what we are going to study today. We're looking at this, right? So this is epsilon 1, this is epsilon 2, epsilon 1, right? Okay, so going up is x direction, z direction, x, y direction, right? We use right-hand rule, x, y, and z. Okay? So this time, we only have HY field, right? We only have HY field. We assume this is transverse magnetic field, right? So it's the transverse magnetic field, and it's propagating in z direction. It's propagating in z direction. So use the Maxwell's equation. We have curl of H equals this epsilon partial H partial T, right? It's the epsilon partial H partial T. And then what we have is, if we take a curl of H, what we have is x direction, y direction, z direction, partial x, partial y, partial z. Right? Then we have HY, and then this 0, 0. Right? This is 0, 0. Okay? Okay. Now we're going to write the HY XZ XZT, right? It's the same thing. So we are going to do the same thing, except now we are working with H field. So it is the magnetic field in Y direction. Let's see what is the difference compared to the TE mode, right? TE mode. So now, okay. So we'll have HM. M stands for the order, right? So you have different orders. So you have first order, second order, third order. MHX exponential, right? I omega t minus beta z, right? So this is time harmonic. This is the propagation, right? Beta is our propagation constant, which related to the dispersion, right? That's the originally we learned from this dispersion, right? Okay, and what is epsilon? So this epsilon I equals ni squared epsilon naught. Epsilon naught is the permittivity, right? Permittivity in the air. This is the permittivity in the glass. It has a relationship, ni squared. Right? Ni squared. Okay. Now let's look at this EZ. Right? So let's do the same thing in EZ direction. Right? So we have EZ direction is EZ direction. Right? So EZ direction is negative I over omega epsilon, right? I over omega epsilon partial H, partial HY, partial X, right? So there is so we only look at the XZ direction. We only look at the Z direction, right? We only look at the Z direction. Okay, so now what we have is this partial, we got the I, right? So we got the I, we have the epsilon. So let me see. we take this partial h. Partial h is this, right? So yeah, I write, I have a, do I have a typo here, right? So this is actually E, right? So this Maxwell equation, this is E, right? So this is E, also has this I omega t term, right? It also has I omega t term. So taking a derivative with respect to t, you get I omega, right? We have I omega and then epsilon. And then you flip to the right-hand side, it become negative I omega epsilon. And then partial hx, partial x in z direction. That's easy. Any questions for this equation? Okay, so now we have this equation. So what we have is now hy should be continuous, right? And then ez is parallel to the interface in the boundary. It also should be continuous, right? Ez should be also continuous. But instead of ez, let's look at hy, right? Hy. So it is equivalently 1 over epsilon partial hy partial x, right? So this is equivalently, this is continuous. Right? So those will be these two continuous at boundary. Right? So it's continuous at the continuous CONTINUOUS. So it's continuous. So this two, HY is continuous, EZ also continuous, which is proportional to, let me write a proportional to 1 over epsilon partial HY partial X, continuous at boundary, right? So those two, we need to satisfy this boundary condition. Questions? Okay. Okay, now we have that and our wave function, right? So I think I have the space here. So wave function. Wave function, HMX, right? So this is HMX. Instead, before the exponential I omega t minus beta z, right? So in this case, we have the HM is HM. Do I have space? Let me write it here. HM, right? HMX. We have 3. Right? So this is still the same thing. A sine HX plus B cosine HX. This X absolute value is less than D over 2. Can you see it? Yeah, hopefully you can see it. And then this will be C exponential negative QX. This is X greater than T over 2, right? Let's say equal, right? D over 2. This D exponential QX, X is less than negative D over 2, right? So this is X on the positive side of this above. So when you see exponential negative QX, right? So in other words, this will be decay, whatever in between, and then decay, right? So this could be sine or could be cosine, but outside is decay, right? Where it's negative axis, is exponential qx, but x is negative. So when x is infinite, this becomes very small number, right? Okay, so now we are going to use those two continuous, right? So it's the boundary, right? Boundary condition. Boundary condition. So the first equation will have hy at, let's do d over 2, right? D over 2. And then we have partial hy, partial x, 1 over epsilon, right? 1 over epsilon at d over 2, right? And then we have hy at negative d over 2, and then 1 over epsilon partial hy, partial x at negative d over 2, right? So you need to first take a derivative, then add 1 over epsilon, right, on the both sides. So we will, we have 4 equations, and then we will simplify, right? Then we will simplify into another 4 equations and solve the problem. So you will, let's do it as an exercise. You will write down, this time you will write down, last time I wrote it down. You assume you all have your notes. Just look back at your notes and write it down, right? So any volunteer for the first equation? I think we have 6 students. So one of you will write first equation, another one will be second equation, third equation, fourth equation. The rest of the 2 will simplify into another 2 equations. Who wants to volunteer to write the first equation? Okay, so how about I'll just look up according to my screen. On the left, I have Caitlin, right? So Caitlin, you will write the first equation. At the second, I have Brent. Brent, you will write the second equation. And third one, according to on my Zoom, Ezekiel, you will write the third equation. And the fourth one, Grayson, you will write the fourth equation. Okay, so 1, 2, 3, 4. And Ben and Josiah, you write the next 2. You will make it simplify, right? Okay. So we'll write. So you just write by yourself, right? The equation you assigned to you, and once you're done, let me know. So once you're done, can you just, if possible, you can either let me know or send a chat box. Either way is fine.
Do you want us to put it in the chat or say it here?
Just if you're done, just say it out. Just okay. Let me know. Yeah, if you're done, let me know. Just go ahead. Say
okay.
It.
A sine hx plus b cosine hx.
So it is now actually at d over 2. There is no x anymore.
So then it
x
would
needs to be replaced by d over 2.
So it is just okay.
Go ahead.
Yeah.
D over 2, right?
Mm-hmm.
Yeah, go ahead.
And then c exponent negative q d over 2.
I'm sorry.
Oh, sorry. The rest of it. b cosine d over 2 then, hd over 2
Okay.
is equal
Equals
to
what?
c exponent negative q d over 2.
Okay. Thank you. Anyone? If you're done, just let me just speak out. So this is my first equation. This is my second equation, third equation, fourth equation. And then we have first equation minus third equation.
Dr. Who?
Yes, go ahead.
Why?
Which equation? Do you have a question? You want to write down the equations?
Yes, sir. But I have a quick question about the first equation.
Go ahead.
Why again was it set to c exponent negative q d over 2?
So you are looking at the d over 2, right? So which you should look at this. So it's basically equal, right? So you should look at this boundary, right?
Okay.
So that's the c exponential negative d. It's a qx, just x replaced by d over 2.
Okay.
Did I answer your question?
Yes, sir.
Sure.
So then for my equation, would it be h a cosine h of x, or I mean h of d over 2?
Thank you.
Minus.
So there is an epsilon, right? So 1 over epsilon. So it's the EZ continuous. So EZ continuous meaning that this piece is continuous. So because the epsilon is different, so this epsilon, so you look at omega is the same, I is the same, negative, we don't care. So the whole thing is continuous, right? The epsilon is different. So we need to include the epsilon from both sides.
So divide that by epsilon?
Yeah, epsilon, should it be epsilon 2 or should it be epsilon 1?
Epsilon 1.
At which region? Is this, so I have region 1, 2, and 3, right?
Oh, I see. That's gonna be epsilon 2.
Yeah, it's inside, right? So we're
Correct.
talking about this field at inside. So it's going to be epsilon 2, right? Okay, so go ahead.
Well, sine, cos,
Sorry.
would it be minus HB sine h of d over 2, and then divide that by epsilon as well?
Epsilon 1 or 2?
That'd be epsilon 2.
Okay, go ahead.
And then that would divide. I'm not quite sure about this last part.
Okay, so last part is at region. What region you are trying to look at it?
That'll be
region 1 or 2 or 3?
2.
Yeah, 2. This one, right? So you first take a derivative. What would it be? You first take a derivative and make x equal to d over 2, and then divide by epsilon.
Let me think. That would just be negative QC exponent. And then Q d over 2, or negative Q d over 2.
Okay. And anything else?
That would be divided by epsilon 1.
Okay. Okay, good.
All right, thank you.
Great. So yeah, so we get this, and then we have 2 plus 4, right? So we have the, I think, what else?
For equation 3,
Yeah, for equation 3, go ahead.
A sine H negative D over 2.
So it's a A sine HD over 2.
Yeah, positive. Excuse me.
Hold on. Hold on. It's the A sine. Yeah. So you're looking at, we're looking at this, right? We're looking at this term, right? So, and then X is negative D. So it's the A sine negative HD over 2, right?
Yes.
Let's move the negative outside. So it's negative A sine D HD over 2. Okay, it's the same thing. Let me just move it out. Go ahead.
And then that would be plus B cosine H. Would that also be the same since it's
Yeah, negative HD over 2,
Yeah.
right? But cosine is an even function, so it's
Right.
negative HD over 2 and positive HD over 2, they're the same.
yes.
Yeah.
And then equals D exponential QX.
Q, you need to make the X.
I'm sorry, D over 2.
Thank you.
Negative D over 2.
Thank you. That's good. So that's good. So I have, hold on. Let me, what is this? Let me close up.
I've got
Okay.
1 minus
Hold on. Let me write Josiah as this equation. Let's ask Ben to work on the last equation, right? The equation 2 plus 4. Okay, you have the last equation here.
Oh, sorry. I was just saying that I could do the 1 minus 3 equation. But I could also try to figure out the 2 plus 4 real quick.
Okay. Either way, if you want to switch, it's fine. They're almost the same. Okay. So
For the 1 minus 3, I'm
okay.
pretty sure.
Can I wait until the Grayson finish it? So we can.
I think I got it.
You think you got it? Yeah. Let's finish
So-
number 4 and then get this too.
All right. So is it 1 over epsilon 1?
So here, right?
Yes.
Yeah. Go ahead.
1 over epsilon 1. Sorry.
Yeah. So we're looking at first at this side, right? At the center side. So are you using the equation for the first piece, second piece, or third piece?
I'm going to use the first and third piece.
Yes, that's good. So now what you want to do this inside the in the core, right? So
Right.
are you using?
Yeah.
Are you going to use epsilon 1 or epsilon 2?
Sorry, epsilon 2.
Thank you.
So
go ahead.
1 over epsilon 2 HA cosine negative H D over 2.
Okay, I'm going to be lazy because negative, I just threw it out.
Okay. And minus BH over epsilon 2 sine HD over 2.
Is inside negative or positive?
Positive.
Oh
wait, negative. I missed a sign.
Yeah, so negative. So I have a negative here. I'll just write the plus.
Yeah.
Okay.
And then is equal to 1 over epsilon 1, or no, 2.
Is
Sorry,
that 1
1.
or 2? So first, are you looking at region 3, right?
Yes.
Region
So that'd
3,
be
should it
1.
be epsilon 1 or epsilon 2?
Epsilon 1.
Thank you. Then
Negative d exponent negative q d over 2.
okay, so we have we take a derivative, right? We take a derivative. There is a q,
Oh yeah, the q.
right? Q, and then we take basically we put it here, right? We take a derivative. Is that region? We should you should it's the negative d, right? So it's the negative d. So meaning that we take a derivative. We take a derivative. Yes, qd over epsilon 1 exponential negative d qd over 2. That's good. Yeah, I think those are the 4 equations. Thank you. Can we do 1 minus 3 and 2 plus 4?
Yeah, so I'm pretty sure 1 minus 3 is 2a sine of hd over 2. And then that would be equal to c minus d, and then exponential negative qd over 2.
That's good. How about 2 plus 4?
I think it would be 2HA over epsilon 2 times cosine of HD over 2 equals QD over epsilon 1. I guess all this could be in parentheses. So QD over epsilon 1 minus QC over epsilon 1.
So it's basically d minus c, right?
Right.
So let
yeah.
me write d minus c instead minus c, negative c minus d. It's the same one, same.
Okay. And then all of
Okay.
that times exponential of minus QD over 2.
Okay, very good, right? So you guys did very good job. So I'll finish the rest of it. Meanwhile, if you haven't copied down the equation, I think you understand how it comes from, right? So that's very good. Just write it down. So it's 1 plus 3, 2b cosine d over 2 c plus d exponential negative qd over 2, and then 2. Then we have hb. So we want to have hb is 4 minus 2. So it's 4 minus 2. So this is 4 minus 2. That's what we have is 2hb over epsilon 2 sine hd over 2 equals qc plus d over epsilon 1, right? Exponential negative qd over 2. Hopefully you can see it. Yeah, kind of barely, right? Okay, great. Yeah, I think you got the main point, right? Okay. Are we all good? Do we need more time to write it down? Okay, I think we're good. So let's come back, right? That's what we learned. So last class we're kind of only looking at TE. Now we look at TM because of this epsilon falling down. So now continuous. I have my HY easy continuous. Instead, I have 1 over epsilon partial HY partial X, right? Previous TE mode, there is no 1 over epsilon term, right? This equation, the only difference is we have epsilon, right? We have epsilon. That's all the difference, right? The derivative contains an epsilon. Okay, so now we have 4 equations. Let's simplify into this form. It's all the same. It's all the same procedure, right? It's all the same procedure. Now let's see what kind of solution it is, right? Okay, so now we get the first set is, right? So the first set is going to be A equals 0, C equals D, right? So A equals 0, C equals D. So C, D, they're the same, A is 0. So, and then the solution is, let's use this equation divided by the second equation, 4 minus 2 divided by 1 plus 4, right? So we get this, and then H, so it will be 2B cancel out. So it will be H tangent HD over 2 equals, so we have epsilon 2 in denominator, let's fall on the top over epsilon 1. This will be the Q, right? So this is the equation for the TM mode. Note that the difference is only this epsilon, right? The difference is only this epsilon, right? The difference is this only epsilon. Okay, now let's use this, right? So this epsilon over epsilon 1 is the index square, so it's n2 square over n1 square epsilon naught. I'm sorry, epsilon naught cancel out, so this is just simply Q, right? So this n2 square over n1 square, right? So this is refractive index, right? This is refractive index. So for example, my glass, right? My glass, the refractive index is about 1.45, 1.5. Air, right? This air is 1, right? And the water is about 1.3. What is index? Index meaning that what light propagating in this particular medium, the speed is divided by the index, right? So, okay, so this is the refractive index, right? Epsilon is permittivity. Right? Okay, so we got the first equation, and then we can have the second set. Now this time it's going to be C equals to minus B. So this time B equals 0 and C equals negative D. And we will do the same thing is H cotangent HD over 2 is, right? So let's have B is 0, C is negative. So let's take a cotangent, right? So it's going to H cotangent HD over 2 equals this negative Q, right? And negative Q, and we have epsilon 1, epsilon 2, right? Let me write it more clear. So it is negative epsilon 2, epsilon 1. I'm sorry. So epsilon 2 is in the numerator, right? Epsilon 2 is in the numerator. Epsilon 1 is in the denominator. Epsilon 1 is in the denominator. Epsilon 2 is in the numerator. And then we have Q. right? And then we have Q. And to the same thing, it's negative N1, N2 square over N1 square Q. So those are the two equations. They are the same as TE mode, except we have extra N2 square, N1 square, N2 square, N1 square here. That's the only difference, but it makes the TM mode. In other words, TE mode is is E field in this direction. Now TM mode, it's the H field is in this direction. It's perpendicular to this white bar. With this difference, we got governing equation, we have extra terms. Okay, I think that's that's it for this equation. But let's do the same thing, right? Let's do the same thing. Is that let me use my previous notes. Let's do the same thing. That now we're going to use. Let me see. Where's my? Yes. Okay. So now let's redefine everything the same, right? Redefine U is HD over 2, V is QD over 2, right? V is QD over 2. So let's just multiply D over 2 on both sides. So we have the first equation, right? So it's U tangent V. I'm sorry, U tangent U. Tangent U is V, right? N2 square over N1 square, right? And then another equation is going to be negative U tangent U equals N2 square N1 square V, right? So if you if you put negative on both left and right hand side, they're the same, right? And we all know that U square plus V square, right? It's the same thing as U square plus V square, right? U square plus V square is going to be same as V square, right? It's a constant, which is N2 square minus N1 square pi D over lambda square, right? So this is the V square, right? And we know that total N number is V over pi divided over 2, right? So for every pi over 2, we get a mode. So it will make it into the, so it's the number of mode, right? So increase to nearest integer, right? So if my V is over pi over 2 become 1.1, so it means 2 mode, 2 solution. If my V is less than pi over 2, is so that N is so that is not dot here. Let's just make this number of mode increase, yes. So the number of mode increase to nearest integer, right? So if the V over pi over 2 is 0.5, that means I have 1 mode. If this V over pi over 2 is 3.5, that means I have 4 modes.
Dr. Who,
Yes.
could you read that line, the second to last line you just wrote? The U
This
squared?
line?
Yeah, that line.
Yeah. So it's the u square plus v square is capital V square. So let me write capital V square. And it is n square, n2 square minus n1 square. And then I have another parenthesis, pi d over lambda square.
Okay. And the line above that, is the right-hand side the same in both of those two lines? In the u tan u and minus u tan u, do those equal?
Yes.
I'm having trouble.
Oh, okay. Yeah, I am. So thank you for pointing out. It's the cotangent u. It's the same as this. Thank you. This
Okay.
is the u, negative u, cotangent u equals the n2 square over n1 square u. Thanks for pointing it out.
N2 squared over n1 squared u.
Oh, n2 square, n1 square v.
Is that little v or capital V?
It's the little v.
Okay. Gotcha. Thank you.
Yeah. Okay. So let's be clear, right? Thanks for, so all this u and v, u is hd over 2, v is qd over 2. So from this two equation, we get u tangent u equals to u tangent u is n2 square over n1 square v. Negative u tangent u is n2 square over n1 square little v. So so this n okay, then my little u square plus v square, right? So let's see how much is h, how much is q. Okay, I need to look up on my notes, right? How much is the h and how much is the q, right? So here it depends on the solution, right? So the q and remember, this is the q and let's say h, right? H is square root of n2 k naught square minus beta square. Q is square root of beta square minus n1 k naught square. Right? So now what we have is this u square plus v square. Right? So this u square is u square plus v square is this h square over 2 square. This will be the d, right? So h square is going to be this over d, and then d square, then h square is going to n2 k naught square minus beta square, right? And then we will add this is v square. V square is d over 2q. So it's plus d square over 2 beta square minus n1 square k naught square, right? So altogether, it becomes d square over 2 square k naught square, beta cancel out. So it's n2 square minus n1 square, right? So how much is the k? This k naught is omega over c equals 2 pi over lambda, right? So this is the propagation constant in the air. So that will be 2 pi over lambda. So it's d pi over lambda square n2 square minus n1 square, right? So that's what we actually did last class, right? Okay, this is a constant. Once we have this parameter, right? Once we have this epsilon 1, epsilon 2 is determined, once this d is determined, this is a constant, right? That's why we said as V. This is V. This is capital V. Yeah. This actually, this equation is the same for the TE mode as we explained last class, right?
Dr.
Yeah.
Who?
Thanks for asking question.
Dr. Who?
Yes.
Should N2 and N1 be squared in that last equation? Or sorry, should the entire parentheses be squared?
Oh, you mean here?
Yeah.
No. So let's take a look. At least I don't think so. So let me check. Where's my equation? That's my equation. This is a V. Yeah. Okay. Let's take a look. Okay.
I think
So are you okay with this equation? Because this is the square root. H is square root.
Yeah, I agree with all of it up until that last point. You just squared it, and I didn't see where you got that from.
Oh, you mean this one?
Yeah.
Oh yeah, it was a mark actually from the previous writing.
No worries.
I have another question as well.
Yeah, go ahead.
Is this supposed to equal V or V squared? Capital V or V squared?
Yeah, you're right. It's supposed to be V capital V square. So it's supposed to capital V square so that U square plus V square is capital V square. So it will make a circle, right? So UV, so it will be the V circle, and this is V. Yeah, thanks for pointing it out. Okay. Okay. Yeah. So this V over capital V. Yeah, this is capital V. This capital V over pi over 2 is the number of modes, right? So now let's come back. Let's come back and let's look at this beta, right? So this beta has a special meaning. That's how it propagates, right? So it's basically it's exponential I beta Z propagation, right? So now let's define an N effective. It's the effective index. Effective index is beta over K naught, right? It's beta over K naught, which is beta over omega over C, right? So let's remove the marker from the previous writing, right? In other words, for example, if I have the index, right? For example, if I have index 1.5, I have index 1.4, index 1.4, what it means is that if I have a glass at 1.4, the light propagating in this medium, it gives the speed, right? So the speed will be V is C over, right? So it's the V here. Let me write. If I have a bulk media, right, index N, right? If I have a bulk media, N is 1.5, that means that speed of light V is C, speed of light in the vacuum divided by N, right? So in other words, for example, if I have the bulk material for my glass, right, the speed of light is actually 3.0010 to the number 10 to the 8th divided by 1.5, right? Divided by 1.5. So now if I have this 1.5, the speed of light in this glass, if it's bulk material, everything is 1.5, it's speed of light divided by 1.5. And if it is 1.4, it will be speed of light in the vacuum divided by 1.4, right? That's how this index is determined. So now I have this mode, right? It's propagating in the waveguide. So effective index is now become beta over K naught. it is usually between the index of 1.5 and 1.4. So that's another important concept. So in other words, the wave propagating inside this waveguide is actually in a speed between the index in the core and index in the center. Is that, do you have any questions? That's called the effective index for that mode of solution. Okay. Okay. So now let's look at, let me share my screen. Okay, let me share my screen. Share screen. Okay, hopefully you all can see my screen. Yeah, okay, great. Okay, so this is the picture I showed you before, right? So this is U, this is V, right? So U and V, this is U tangent U equal to V. This curve is U cotangent U equal to negative V, right? So this line, this solid line is the symmetric solution. This dashed line is the anti-symmetric solution. So this circle, right, a quarter circle is the V square. So it's U square plus V square equals capital V square, right? Capital V square. And in this case, we will have, in this case, we have to satisfy both solutions, right? We have to satisfy, if you can see me on my screen, you have to satisfy both U tangent U and U square plus V square is capital V square. So depending on what is capital V square, let's use this as an example. Hopefully you can see my mouse. And we have 1, 2, 3, 4 solution. So each solution corresponding to different electromagnetic wave. So we call it mode. One mode, meaning that, so if we have 1, 2, 3, 4, it depending on different V, right? What is V? What is capital V? It depends on D, the thickness, wavelength, to refractive index, right? To refractive index. So now let's take a look. So if I have this N1 is 1.5, N2 is 1.6, D is 5 micron, wavelength is 1.55. We get 4 solutions. So this is called TE0, TE1, TE2, TE3. So those are the solution here, here, there, and there, right? How to solve it? So once we find the intersection, we'll find this intersection when they agree. Once we have this U and V, we can come back to get Q, H and Q, right? Once we have H and Q, we can find this beta, right? So what is the beta? And beta, we can use beta to find effective index. I didn't mark the effective index here. Okay, and then once you have H and Q, and then you can have this solution, right? H and Q, you can come back to my original solution. It's exponential. Can you see my? Okay, so you can write it down either A sine HD over 2, right? Plus B cosine HD over 2, right? And then all you have C exponential negative HD QX and D exponential, this negative is QX, right? So you can go back to here to find the mode. Once you write it down, you get you get this mode. You get this shape, right? So you can see that it's continuous, right? We know that E is continuous, or H is continuous, and also derivative is also continuous. Questions? We're good? Okay, so let's move on. Okay, so now due to the difference between TE and TM, right? So this curve, you can also say, so the V, right? So in here is one solution. Once this circle has another intersection with this dash curve, when capital V is more than pi over 2, so it's the tangent and cotangent. This is pi over 2, this is pi, this is 3 pi over 2, right? So once V is pi over 2, you get another mode. So V over pi over 2 determine how many modes you have. So V divided by V over pi over 2, this n, right? If this number is 0.5, that means one mode, right? Because there's always one intersection. If this V over pi over 2 is 1.5, that means two modes. And then in this case, right, it's the 4.2 or something. So we a 3.2, so we get 4 modes, right? So you can determine how many modes according to capital V. Okay, so now we will write the V, right? We will write this V, capital V. We can find this effective index, right? Effective index, we plot the effective index as a function of capital V. So use the different criteria, N2 is 2, N1 is 1.5, right? And now we can find out the TE and TM mode, right? Remember the last class, we find the solution for the TE. This class, we find the solution for the TM. The difference is only N2 square over N1 square, right? So, we can find either TE or TM, right? And they have the same cutoff condition, right? Are similar, right? And Q over 2, N2 over N1. Okay, then we have the going down. Okay, so we could also have anti-symmetric. So we have I'm not anti-symmetric, sorry. Previously, we always deal with this epsilon 1. On the other side, it's also epsilon 1. So we have either symmetric or anti-symmetric. But now we could have asymmetric case. So this is 1.7, this is 1, this is 2. So you can see that mode, because it has lower index, mode has more leakage, have more tail on the left-hand side than the right-hand side, right? So it could be the case that it will lean more towards on the left-hand side, right? Okay, please feel free to interrupt me if you have questions. Okay, so now we'll deal with optical fiber. The optical fiber is way more complicated, right? Way more complicated. You think about it, right? The SlabWaveguide, we only have one dimension. It has the it has sine, cosine in the center, exponential at outside, sine, cosine, and exponential at outside, right? So even with this one-dimensional problem, it's rather more complicated, and we have to have this mode, exponential and sine, cosine. But if we have a circular structure, we need to solve circular cylindrical coordinate, right? Circular structure. So it's a 2D problem, right? It's a 2D problem. And solution in this case become Bessel function. the solution is instead of cosine, sine, or the exponential, it is the Bessel function. And this we won't get into the detail. But one thing we want to just let you know, the solution is this is the Bessel function as a function of radius r, right? So we could have a scalar mode or vector mode. A scalar mode is an approximation. So one would do some approximation to have some simple solution, versus the vector mode is the true solution, is the total solution. Okay, so this consider as it's called linearly polarized mode. So this is an approximation. This is if we do the HE mode, TE mode, HE 2-1 mode, TE TM0 mode. This is the vector mode. You probably learned something from this 3337, right? The electromagnetic wave class. You can have this TE TM mode. It's very similar, but over there it's the metal waveguide. Here we use dielectric waveguide. It's just very similar concept, but different solution, right? But very similar. Okay, so you could have this circular structure. You could have just the Gaussian, just one mode, right? Here you have a sideband. Here you have 2 or 3 sideband. Now you split into two sides, right? 4. So left, right, up and down. So now it's hexagonal. That's octagon something, right? It's going up and up. So it's become more and more complicated. And on this vertical, you just split into more side lobes. On this side, horizontal, on the left and right side, you have more oscillation, right? You have more oscillation. On the up, you get more sideband, right? So this is more and more, you can have more and more solution, right? In other words, you can have more and more modes. Each mode corresponding one electromagnetic corresponding to one electromagnetic wave representation, right? Okay, so it's just the same thing. At the end, I want to actually talk about one more thing, is that it is a linear, Maxwell equation is a linear function, right? It's a linear solution. So let me use this. It's a linear solution. So for example, right, this curl of H is epsilon partial E partial T, right? So if I multiply by a factor of 2, so 2H, right, equals epsilon 2E over T, it is still a solution. So when we plot this mode field, right? So this is the first mode, this is the second mode, right? And if we actually multiply or divide, and then as long as the shape is the same, so this will be divided. So if this will be fx divided by 2, it is also a solution. So whether the absolute value, it doesn't matter, as long as it preserves the shape, right? As long as it preserves the shape. And at the boundary, right, you can see it's continuous. And also derivative is also continuous. Why? Because we write down all the equations, right? I mean, we all did it together. You write down this equation and we lead to U tangent U. This equation is coming from this condition, back boundary condition, so that the the field is going to be continuous and the derivative is also continuous. If it turns out that here is not continuous, then you have something wrong in your code or something wrong in your something wrong in your solution, right? So next class we'll have a lab session. Next class we have a lab session, right? So we'll learn it all together.